All right. Hello, everyone. Welcome back to Comp 2160 Programming Practices. I see that we are all looking like we are halfway through a term right now. Yeah. We are almost halfway through the term. We're not quite halfway through the term, but we're getting very close to halfway through the term. And I was thinking as I was coming in this morning that it feels like it's been such a long time since I've seen all of you. But the reality is, like, if this were a Tuesday, Thursday class in a regular term, this would just be the amount of time that we wouldn't see each other for. That's just it. It's just that normal Thursday to Tuesday transition. But it feels like it's been a long time since I saw you because we're seeing each other so often. I know you had a Comp 2160 assignment due on Friday, and I think you have a 2080 assignment due today. Yeah, so I guess if you are taking 2080, I hope that that's going okay for your assignment today. I hope that you were able to spend some time outside on the weekend when it wasn't raining. I went to a fair with my kids yesterday, close to where I live. There happened to be two different fairs set up. Like, one was set up in this community club, and then the other one was set up at the Red River X Fairgrounds. And they were both supposed to be open all weekend. And we went to the one that was closest to my house. And we pulled up at around 1 o'clock yesterday afternoon. And they were supposed to be open till 5. And it was completely already shut down. Like, they just taken everything away already. And this is an extremely unrelatable anecdote, but when you take a 5-year-old and you say, yeah, we're going to the fair, and we get to the field and it's just an empty field, that kind of results in tears. So I'm grateful that there was another fair that we could go to, and we went to this other fair. And this is another completely unrelatable anecdote, but at a certain age, maybe you're there already and maybe not, but at a certain age, when you get on those rides that spin around really fast, you start to feel queasy after it, and like not just for a little bit, but for a long time. So like yesterday afternoon, I went on the Sizzler. Do you know what the Sizzler is? Does anybody not know what the Sizzler is? Okay, so it's the ride where it's got 4 arms that go out, kind of at a cross like this. And then at the end of each of these arms is 4 bucket seats on another cross. And so the bucket seats are spinning around, and the big arms are also spinning around at the same time. And this is my son's favorite ride. It's his favorite ride, but he's also too small to go on by himself. And so somebody has to go on with him. And so I got on that ride, and I spent the next hour and a half or so feeling pretty queasy.
You ever try to high-five the people?
Well, so like, do I ever try to high-five the people? As I'm going around, the ride operator is sitting, looking extremely bored. And as you go around on this ride, you are just like whipping around really fast. And so like at certain points during the orbit of this ride, you're whipping around really fast, and you're just like screaming toward the ride operator. And he's just sitting there like, I'm bored because this is my job. And I'm going there like, I'm approaching you at about 70 kilometers an hour right now, and we're this far away from each other. And so no, I didn't think about giving him a high five because I thought that might hurt. I hope that you all had a good weekend despite assignments. I hope that you had a good weekend despite weather. I hope that you're all doing okay. Let's keep on trucking on with Comp 2160. So today we are going to be working on strings.c from lecture 8. We're going to spend some time reviewing this code before we start changing it. So we will have a chance to look at it. We're going to do a couple of things before we get to looking at this code, but we are going to work on this code. So please have it ready in your editor if you want to follow along with what we're doing. Before I talk about learning outcomes for today, I do want to point at a couple of things on our course homepage. So on the content section for our course homepage, there will be a sample solution for assignment 1 published at the end of the day today. So it'll be available for you to take a look at after 4 p.m. today. I am happy to answer any questions or concerns that you might have about my sample solution compared to your sample solution. but I'm going to remind you that in terms of the way that your assignments are being assessed, is that the graders are using these rubrics. So they are using those rubrics. The sample solution is there as a guide for them to see approximately what it could look like, but these rubrics are what the graders are using to assess your work. So in terms of making sure that you're meeting what's required for the assignment, look less at the sample solution and a lot more at what these rubrics are saying about what your code should look like and what it should do to get a sense of how you're being assessed. But if you got stuck on something and you're not sure how to get past it, please feel free to take a look at the sample solution. Sample solutions, for the record, are for your personal use for the course. They're not meant to be published in any other places. I can't, of course, stop you from publishing it in other places, but it's technically my copyright that's on that sample solution, so please respect that. The other thing that I want to point at in terms of assignments is that a description for assignment 2 has been posted. I've posted this for you so that you have access to it. You can start reading it if you want to. I will discuss this assignment in class on Monday next week. I want to make sure that we are ready for the term test on Friday before I spend any time talking about the assignment. But the assignment description is up. We're going to keep working on stuff today that will be related to this assignment description. We're going to keep working on stuff on Wednesday that's related to this assignment description. And we will talk a little bit more on Tuesday about, or on Monday next week for stuff that's related to this assignment. So it's up, it's available for you to read. I will talk about it next week. I'm just not going to talk about it this week in terms of the term test. The other thing that I want to say related to the course webpage today is that I will record a video for tomorrow's lecture. So I will post something up on the course webpage related to tomorrow's lecture. And the idea here is that I'd like you to watch it before you come to class on Thursday, and then we'll quickly review stuff on Thursday, and we will, maybe have a little quiz to check out on things, how things are going, have time for you to ask questions yourselves about what's in the video before we get going. And then on Thursday, we'll also spend some time talking about the term test that's happening on Friday. Are there any questions about anything before we get into stuff for today? All right. Okay, cool. So let's pop back up to the slides here. By the end of today's lecture, what you should be able to do is we're going to be continuing this. So we started to do this last week on Thursday, where we started to build the string class or the string object or the string data type. What I want us to be able to do today is I want you to be able to design and use interfaces in C specifically. You may have done a little bit of this in Java with the Java interface type, but there really aren't interface types in C. We will look at how to do this, how to approximate what Java is doing in C using something called a header file. I want you to be able to hide implementation details of a data structure that implements an abstract data type with headers and separate compilation. So every program that we've written so far in this class has been able to be compiled with just one single command. So we run Clang, it takes the code that we've written in a .c file and it produces a program for us. This is kind of related to what we were doing last week with the phases of compilation. We're going to be building object files, so code that is compiled but is not runnable, and those object files will be representing the library that we're building. And then we're going to have a separate C file that will implement a main function. So this is the code that actually does the work that we want. We're going to have to separate all those things out. So we're going to have 2 or more commands now to compile programs with our C programs. And we're going to be forced to use dynamic memory allocation today. Everything that we've done so far in C has been a stack allocated variable. So we declare arrays on the stack, we're declaring primitive types on the stack, and at this point now we're declaring structures on the stack. We're going to be forced to do dynamic memory allocation when we get to hiding the details of a data structure, because well, I'll get to that point when we get there, but we're going to be forced to do it in today's lecture when we're starting to think about separating out our interface and our implementation. Before we do that, let's have a little quiz on redirecting I/O. So this is one of the last topics that we had last week, or one of the topics that we had last week. I'll give you like 5 more seconds to join. Okay, the code should stay at the top for the rest of the game, so if you're joining late, you should still be able to join. Here's the first question. Okay, awesome. Okay, great. So lots of people are getting this. If I want to redirect to standard output, I'm using that greater than symbol. I like to think of this as a mouth. The mouth is eating the thing that we're trying to, I don't know, consume. And then it's, I don't know where to go with this because then it's the end of the digestive system that's like putting it into the file. So I think of it as a mouth. Change the source code to write to a file. This is, in my mind, this is the wrong answer. This is the right. You could do this. Sure, you could do this, but you don't necessarily have the source code. You can do input and output redirection without the source code. You don't have to have the source code to be able to change a program that already calls printf or fgetS or any of the other input or outputs that go to standard input or outputs. Here's the next question. Okay, which operators should I use? Which operator should I use? So both of these are right. Both of these are absolutely right. I could redirect output to a file and then redirect that file to be the input of the next program. I could do this as a two-step thing. Piping is the other correct answer here. This is the other correct answer in terms of I don't want to make an extra file. I just want to send output from one program directly to the input of another program. But that first option definitely works as well. We could do this as a two-stage thing. Cake is the fastest. What? It says cake is the fastest. Thank you very much. D's just happens to be on top. D's what? Yeah, D's what? Okay. Okay, so in this case, both of these would work if we have no restrictions. I could do the two-phase redirect output and then redirect input, or I could do the pipe. But when I add this restriction here, I'm not allowed to make files in the directory. So examples could be that the file system, so you brought your computer up, and it's able to read all the files, but you cannot write. It's a read-only file system. This is something that could happen if, for example, you are putting something into production. You've written some software with your team, and you're putting it up into production, and your production environment is a read-only environment. You don't want someone that's able to break into your system to make changes to your source code that's running on your server. Or you run out of disk space. You can't make any more files. Or the amount of data that the program that you have on the first side is generating so much data that you cannot write that much data to disk. If I can't make files in my directory, then this pipe symbol, that pipe symbol, doesn't make extra files. It just goes directly from one program into the next program. fgetS and printf are basically just plugged into each other here. We don't have extra files that are being generated in between those. That's good. Here's the last question. Okay, awesome. So yes, there's something that's saying like, what do you want for this option? And then what do you want for this option? And then what do you want for this option? And then what do you want for this option? Should I turn this on? Should I turn this off? Should I print your name out? What should I do? I want to just fill up a file with all of the answers to that and then redirect standard input to be that file. This one is potentially correct. Change the program to read a configuration file. That, in the long term might be a better choice to have an additional option. But again, if we don't have the source code, we just have the program, redirecting to standard input is going to be the best option here. Let's take a look at our final leaderboard. Now Cake is the fastest and the best. Yes, congratulations, Cake. I'm also really delighted to see Pakachu up there. Thanks for getting that reference. Are there any questions about any of these questions or answers before we move on? You all did very well, so I'm pretty happy with that. Retry. Now that you know the answer, retry. Okay, awesome. All right. Let's continue to build our own string data type. This is the thing that we did last week. We created the strings.c file. We declared and defined a string structure that has two properties. We wrote a main function that populates it. And then we started to write some functions that replicate string methods from Java's string class. I'm going to pop this open. So here's strings.c from last class. The back, is this big enough for you? Thumbs up. Is that okay? Thank you. This is our string struct. What we've done so far is we've defined the structure, we've declared it, and we've defined it here. The string structure that we've got has an array of characters and a length property. C doesn't have a constructor. There's no methods. There's no classes. So we don't have that special method attached to a class definition that would give us an instance of that. So we've created our own thing that's a function that returns an instance of that string structure. It takes as input an array and a number of characters that are being passed to it. And we wrote a charat function. The charat function here returns a character. It takes as input a string instance and and an index that we want to accept. There are a couple of things here that I've done where I've started to make statements about the assumptions that I have of code or values that are coming into my function. I've started to say things here in my comments like, this has to be greater than or equal to 0. An index into a string must be greater than or equal to 0, and it must be less than the length of the string. I'm starting to write these assumptions out because I'm starting to want to think about these assumptions. We're going to think a lot more about this in Design by Contract, but this is a preview of that. And I'm going to continue to write these kinds of comments in my blocks above function prototypes. The thing that our function here returns is that it returns a character that's at the index that's specified, or a null byte if you've passed an invalid index to this function. So if you violate either of these assumptions here, you're going to get a null byte back from this function. Within the main function here, we've got some code that creates an instance of that structure. So on line 38 here, we're declaring a variable that's called string with the type struct string. We're making an instance of it by calling make string on line 41, and then we're printing out some stuff. And on line 46, we're also calling char at. At the very bottom here, we've got the constructor function. So lines 51 through 70 are the constructor function that we've got. We're declaring an instance of this string structure, and then we're also initializing the whole thing to 0. Structures can be initialized in their entirety, so all the amount of space that's being used for that structure on the stack can be populated with 0. This is good. We want to have a string array that's filled with zeros, null bytes, and its length by default should also be 0. So if we fill the entire structure up with 0, we're going to accomplish that. Within here, on line 61, we're starting to do something called defensive programming. We're testing to see if the values that are being passed to us are reasonable in terms of the assumptions that we have made. So in our string structure, we've declared this max string length to be the maximum number of characters. This is as big as the array can be for that structure. We're also checking to make sure that numchars is greater than 0. There's something that's being passed here, and only then are we going to actually use this string copy function to copy stuff into our array. If either of these cases is not true, then what this function is going to return is a string that has 0 length with 0 characters in it. So they'll all be null bytes. So if we tried to refer to any of those bytes, it would just give us a null byte back. This function here, it looks a little bit weird. There's one kind of weird thing about this. I mean, it might look weird for lots of reasons, but there's one specific weird thing that I'm thinking about here. I'm going to go up to the very top of my file here to where I define what a struct string is. I'm defining a struct string as an array of characters and a length. I'm going to go back down to make string. So I'm searching with Vim here. To search with Vim, you can press the / on your keyboard, / and then start typing, make string. And then if I want to get to the next instance of that, so I pressed enter. If I want to get to the next match, I can press N on my keyboard and N on my keyboard, and it will take me to the next string that matches that. So this string structure has an array of characters in it. I've declared on line 56 a struct string as a stack allocated variable. Previously, when we were talking about arrays, I said you cannot return an array from a function. You can't do it. You cannot return stack allocated arrays from a function. Then we tried to put char, square brackets, and compile time error. We can't do that. What is this function doing? It's returning an array, a stack allocated array from a function. That's kind of weird. That is kind of weird. A struct is not an address. It is an object. It's not a class. It's an object. It's a thing, a chunk of memory that's been allocated that has space and has named parts of that space. When I return a struct instance from a function, the contents of the structure are copied into the place that I'm assigning it to. So if I go up here to where I've assigned this string value, the structure that's returned from make string is going to be copied into the struct that's been declared on line 38. So that structure in the function is stack allocated. When that function gets popped off the stack, it does go away, but because of this semantic of I'm going to copy the contents of structs around, it works, and there are no warnings. We don't get issues with the value that you tried to return has been allocated on the stack. There's no warning there. It just works because those contents are copied around. This is great. I'll get you in a second. This is really great because it's kind of simplifies some of the stuff that we're doing. But the problem with it is it's copying stuff. It's copying everything that's in that structure. So if I have 100 characters, or if I had 1,000,000 characters in that string, it would have to copy 1,000,000 characters. No matter what, if I've only populated 5 characters, it's going to have to copy the entire array every single time I return it from that function. Yeah?
I'm guessing there's 2 different stack frames, one for make string and one for the structure of string. And then all of a sudden that was a pause, and that was just one.
Yeah.
There's 2 of them.
Yeah. So when we're in main, we have a stack frame for main, and the stack frame for main has space for argc, argv, and the entire structure for string here. When I call make string, I'm pushing onto that runtime stack this function, which now has space for characters, numchars, and then another space for a completely separate string. This isn't me passing an address anymore. This is going to be, there's an entire copy of a structure on the call stack for this function now. So now there's 2 copies. When we get to the return statement, it's going to copy the contents of the structure that's in this stack frame into the one that's on main, and then it will be popped off. So now there's only one copy of a string, and all of its contents have been populated by copying from what was on the stack in the make string function. Yeah. Any other questions? Okay, we're not going to leave it this way for very long. Again, we're going to be forced to start using dynamic allocation to do this. But for now, this is kind of weird. And this does kind of get us around that we can't return arrays from functions. But we're not going to have that problem for much longer anyway. So that was one weird thing. The other thing to look at here is in terms of charat. This isn't weird. This is just, again, kind of a best practice. I want to make sure that when I'm taking inputs from a function, I'm working with arrays here. I'm working with values that are being passed to me, referring to the array that's in here. I want to defensively code here. I want to check to make sure that the value that has been passed to me actually fits within the bounds of what I'm expecting it to. Okay, any questions about strings so far? We're all doing okay? What are you doing in 2080 right now? Asymptotic notation. Okay, so it has nothing to do with strings, not even a little bit. Cool. All right, so this is our string code so far. We're going to change the way that we were writing this. Our string code it's not very big. Like, we've got 3 functions, and we have a structure that's got 2 properties in it. This is a really small piece of code right now. But over time, programs are going to get very big, especially when you're starting to work on teams of people. So you get into software engineering in 3rd year, you get co-op jobs starting in your 3rd year. After you graduate, you start working on a team, working on software, and these programs and code that you're writing are very, very quickly going to get very big. The problem with big code is that it's really difficult to understand in its entirety. So there's a lot of software that's installed on my laptop right now. One of them is my operating system. The Linux kernel is part of that operating system. The Linux kernel has something like 20 million lines of source code, which is unimaginably big. Understanding that in its entirety is not possible. There's so much going on there that it's just not conceivable for me to understand that. Linus, that very friendly gentleman that was extending his middle digit at us before, it's almost, in my mind, maybe he does, maybe I'm misjudging him and mischaracterizing him, but I don't think he understands everything in the kernel in its entirety anymore. Even if he's the original author, I don't think that he is able to, just because there's so many moving parts. It's difficult to understand in its entirety. If we've got one massive file that's thousands and thousands of lines long, it gets to be pretty difficult for multiple people to start working on different parts of the code base. There's also going to be a bunch of reusable structures and concepts that we have within a single program, where we don't want to have to like copy and paste big chunks of things to re-represent those same ideas over and over again. So we're going to try and do this thing called modular design. The goals with modular design are, we want to have a bunch of smaller and easier to understand components. The word component here is not program. We're not talking about programs anymore. We're starting to talk about small, reusable chunks of code that by themselves don't do anything, but we can use them for stuff. Smaller, easier to understand components. And then a benefit of this and a goal is that different people can work together on the same piece of same project without having to stomp all over each other in terms of the code that they're working on. We also want to, again, extract these reusable structures and concepts. You have done this. You've been on the receiving end of modular design lots in the programming that you have done so far in the courses that you've taken. You've used libraries extensively in your development. There's this great library in Java that's called system. System represents, actually literally just represents your system, and then there's a bunch of stuff that you can do to interact with your system through that class. One of the properties that the system class has in Java is this output stream, standard output, and you can call println on it. You can get it to do stuff. Does anyone know how that works? You do? No, what does println actually do? It puts characters on, okay, yeah, that's what it does. How does it work? Has anyone used processing before? Yeah, do you know how that works? Do you know how we go from ellipse 250, 250, 50, 50 to having a circle drawn on our screen? Okay, so you're saying lots of words that are related to how it might be implemented, but has anyone looked at the processing source code before? Inheritance might be part of this, but not really. For anyone who took Comp 1012, np.linspace gives this a linear array, a NumPy array that has values that are spaced equally between all of these points. Does anyone know how this works? I don't have any idea how any of these work. I don't know. I don't really know. And I don't even really care that I don't know. What I'm getting from all of you right now is that you know what the effect of calling these methods and functions are. You know what they accomplish, and that's enough. You have a library of code that you're able to use in your own code. You're able to call those library methods and functions. Stuff happens that you want to happen, and it works, and you don't really care about what it does under the hood. And I'll answer this for you. No, you don't really need to care. You really don't need to care, unless you're super interested in knowing about like drawing graphics primitives and actually printing out circles on the screen, or figuring out how to divide a space evenly on a linear plane. There are two main parts to this idea of modular design that we're going to be focusing on. There's the interface of the idea that we are trying to build. And then there's the implementation of the idea that we are trying to build. Again, we've been building programs. This might be a little bit of a review from 1020 in terms of seeing the word interfaces here. But I want to formally separate these two things. There's the part that somebody else sees, system.out.println, np.linspace, ellipse. There's the part that I see as someone that's using the library, the interface, and then there's the implementation, the code that actually accomplishes that thing. Our goal is to take everything that we've been doing so far in C and separate them into two physically different pieces. Yeah. Yes, yes, yes. We're going to talk about it in just a second. You are on the right track. You are on the right track. You're definitely on the right track, though. Okay. Yeah.
Interface is like an overloaded term, isn't it? Like, it means like the data, like type, and then also interface, and like interface, like separate, right?
Take 30 seconds, and I want you to think about this word because it's overloaded. Yes, it's overloaded. Take 30 seconds. I'm not asking for responses. I'm not asking for you to write anything down. I just want you to think about this. Does everybody know what this is? This is a video card, it's a graphics card. When you've got a computer that you want to have some kind of graphical output on, you got that main board again. We talked about memory being RAM. These are expansion cards that you plug in to populate how much available random access memory you've got. A video card like this, or a graphics card, is another expansion card that you can plug into a slot. And on one side, you can plug in your monitors, and on the other side, you can start doing stuff here. Play video games, mine Bitcoin, or do AI, or whatever you're doing. This here, this part right here, this is a literal physical interface. It's a literal physical interface. The plugs that you see there, the standard that they implement is called DVI. There's also an S-Video interface there, a little circular plug that has a black connector. That's called S-Video. This is a literal physical interface. A monitor is able to plug a cable into this, a person. The monitor doesn't plug the cable in, the person plugs the cable in. A person is able to plug a cable into this, and the monitor that's on the other side, the display that's on the other side, it doesn't have to know or care at all about how that part works. It doesn't have to know anything about that. I'm able to just jam a cable into there and get a picture on my screen. This part is the literal physical interface between my monitor and then the way that all of this stuff works in terms of like how NVIDIA has decided to engineer chips that will create these signals that go out to my monitor. That's a literal physical interface there. In terms of the things that we're thinking about with code, an interface is going to be only public function signatures or prototypes. So in terms of this picture that we've got here of a graphics card, the only thing that's on this interface is the public interface being those plugs that I can plug into. We are going to have data type declarations. Let's look at strings here really, really quickly. I'm going to go back up to the top. My struct string here is a declaration of a type and a definition of a type. So this is the same in Java as having a class. I'm declaring a class as being able to be used, and I'm defining the contents of that class. I'm declaring a structure that's called string struct, and I'm also defining the contents of that structure. An interface in C will only have the declaration part of that. A declaration of a type in C looks a little bit like this. This is one way that we can do a type declaration. We're going to add a new keyword to our arsenal here. It's called typedef. Typedef is type define. Struct string is going to be the type of structure that we are defining or redefining, and this is the name that we're going to give it. This accomplishes two things for us. One, it declares the type for us to be able to use it in other places. And two, it means that I no longer have to type out struct string anymore. I can actually just type out string here. So it's accomplishing two things for us. The interface that I'm going to define for my abstract data type has a type declaration, but it does not have a definition. So I put a semicolon immediately after that. I don't have curly braces and properties in my interface that define what is inside of this thing. I am now trying to hide the way that this is implemented from someone that's using this library. I don't want them to know what the insides of my string look like. This is really going to be the minimal set of information that you need to know to use the thing, where the thing here is the abstract data type that you're implementing. The implementation now is going to be physically separated from the interface that we've got. The implementation is going to have the implementation of functions. These functions can be both public implementations, so the things that we've declared in our interface, and private things, so stuff that could be supporting the library that we're building. We're going to have data type definitions, so the actual contents of what this structure is going to look like so. We're going to talk a little bit about this, where I'm going to go through a kind of a process of how do I take these things apart? How do I get this one C file that has both my implementation and interface together? How do I separate those apart? There are two places that we can think about this. One of them is called functional decomposition. And this is like, how do I take the concept of a string and separate it out into an interface and an implementation? And then the other part is going to be, how do I physically do that? So how do I accomplish this with multiple files in a C program? And then how do I compile it again? Okay, so functional decomposition here. The general idea is identify the data model, the thing that you're trying to represent. Identify the data model. Identify any invariants. This is a word that we're going to see again. I'm going to quickly define it here. An invariant is a property of the data model that says whether it's valid or not valid. So if I were to take any instance of a structure and look at its contents, do I know if it actually meets what it's supposed to meet? What is it supposed to be? We're going to look at this word again when we get to design by contract, but it's ultimately just checking to see if the structure that you've got is actually valid. And then start to think about how the data that you've got is going to be given to you, what transformations might need to be made on the data, and what output you're going to have from the functions or code that you're ultimately writing. When you're thinking about data models, a good way to come up with a data model initially is to think about what you're being asked to represent. So if you're given a file as input, what's in the file? What are the logical things that you're trying to represent that are inside that file? This is getting down into what primitive data types represent the information that you're being given. So if you can represent this all as arrays of integers, you could do that. Or should you be building compound data types, so like structures in C or classes in Java or Python? Then, once you have a representation of the data that you are going to be working with, it's going to be thinking about what you're going to be doing in terms of manipulations to that data structure. So what kind of input do I have? How do you get that input? How do you transform it to your internal data model? What operations might someone else need to be able to do to that? What are the public operations that they need to do? And then what that ultimately gives us is the interface for what we've got. The way that we're going to implement just the interface is to use a header file, so a .h file in C. A header file contains just function prototypes, forward declarations. It contains structured declarations with that special typedef keyword as necessary. There are some types that you don't want to put in your header. Let me give you an example of that very quickly that we will revisit again later. If I'm implementing something with a list underneath, I don't want to put the list data type in my interface. I don't want someone to know that I'm internally using a list to represent something. If I'm using an array to represent something, I don't want to put the array in the interface because I don't want someone to know that I'm using an array to implement this thing. That's private information for the code that I'm writing to implement the library. It's not important for someone who's using my code to be able to know that information. Ultimately, we're trying to make sure that we are not exposing any internal implementation details. I'm going to give you, again, just 20 seconds right now. Just think about this. And then we're going to start trying to do this. We're going to start to try and extract the interface for strings. Okay. We still have to implement it. So we went through those 4 phases of compilation. We went through preprocessor, code generator, assembler, and then linker. We were able to write C programs that we got ultimately to the end with just a function prototype. We didn't actually have a definition of a function, but we kind of actually have to have that if we want to have code that compiles. We still need to implement these functions. So we're going to write these C files that will implement the prototypes. They will not have a main function. They will just have the code for the library that we're trying to build. In all of the C files that we're using, so we're going to have a main one, and then we're going to have one for our library. We're going to use the include preprocessor directive to use our header file. We're going to define the functions that we've got. And then we're going to have all of our internal implementation details, including the structure definition itself. In a different C file, the main function, where the main function lives, I want to use this include preprocessor directive to get the .h file that has all my functions that have been forward declared. And let's try to do this. I want to do this right now. I'm just going to start typing. I'm going to annotate what I'm doing as I'm doing it. I invite you to go along with me as we are doing this. So I'm going to pop open my terminal here. I'm going to open another terminal to the side. And I'm going to change into my, my source code directory. This is lecture 9. And in here, I'm going to make a new file. So right now I've got strings.c. I'm going to make a new file right beside this one that's called strings.h. This is the public interface. This is the public interface for my string type in C. The public interface for my string type in C is that someone that's using my library needs to know that there is a string type. That's the public interface. The private part is that they don't need to know what the actual contents of that structure are. So I'm going to say here, type def, struct string, string. This declares a string type for use, but does not expose how that string type is implemented. This also has this double meaning of, now I can just use string as a bare word in my program to declare a variable. So I can do something like string my string. I don't have to put that struct string keyword there anymore. I'm going to go back to my strings.c. If I'm going to hide what this looks like inside, I need to give someone the ability to create an instance of that. They can't declare it anymore and then just populate it themselves. They must call my function to be able to do that. So part of my public interface here is my constructor function. So again, I'm not doing struct string here because I've done that type def, so I can just use string. But I want my function signature to be the same, characters and length. It's just a forward declaration. I'll copy these comments to this header file after class. I'm not writing them right now, but I will just copy completely the comments that are in strings.c to the header file after class. We okay with this so far? Yeah.
Does so for this one, you have it as length, and on the other one, you have it as numchar?
Ah, thanks.
Okay, so let's do that.
That's not on purpose. Did I call it numchars? Oh, it's right there. I wrote these comments and they're right there. It should be numchars. I'm not trying to make them different. I'm trying to make them identical. Yeah. Okay. The other part of my public interface so far is my char at function. So I'm going to say char at string. I don't need to use struct string anymore because I have forward declared, or I've pre-declared this type. I also can't use string as a variable name anymore because that's the name of my type. So I'm going to say my string here. In terms of, assumptions that I'm making about index, in terms of assumptions that I'm making about numchars, these are still the same across both of these things. For everything that I've got here, that's my public interface. That's it. That's the whole public interface that I've got for this. So I'm going to save this on this side. I've got strings.c over here. And I'm going to do one more thing here. I'm going to create another file. So I'll put this down here. I'm going to go to this lecture, I'm going to make a file called main.c. I will copy my templates. Whoops. I'll copy my template to be main.c here. So in this directory right now, I have 3 files. I've got main.c, strings.c, and strings.h. If you are copying along here, please make sure you're using strings and not string, because there's already a string.h. We want to make sure that we've got a different name for what we're working with. So I'm going to edit main.c. I'm going to delete these comments here. And I'm going to start by including the forward declarations and type declarations so that I can use this library in my main function. We're going to use that include preprocessor directive, but it's going to be slightly different than what we've been doing before. We're not using angle brackets anymore. These angle brackets say these are libraries that are installed at the system level. So stdio.h, stdlib.h, and stdbool.h, these exist in a folder that is, I believe it's under /user/include. We want to look in the current directory for the header that we're going to be using. So we're going to use double quotes here. I'm going to say number include strings.h. Double quotes means look in this directory for the header file. I'm going to save this. Preprocessor directive here. It is a text replacement engine. It will literally take the contents of strings.h and replace line 7 with all 19 lines of what's in string.h right now. It just inserts that whole thing into there. So what we had been doing before in strings.c is we declared our type at the top, we did a bunch of forward declarations, and then we had our main function. Now we're going to have our type declaration at the top, our forward declarations for functions, and then our main function. So structurally, it's the same as what we had before. So I'm going to write this out. I'm going to quit strings.c for now. And I want to start compiling this. I want to start compiling this. So what I'm going to do right now is I'm going to say clang wall main.c -o main. All I have here is main and strings.h. In my main function, I have not used any of strings.h, so this compiles successfully. It's not looking for function implementations. It's not trying to use types. It just works because I haven't actually called anything. Here is our first problem, string my string. I'm going to declare an instance of this string. I'll try to compile this again. And we get a compile time error. The compile time error says, variable has incomplete type, string, aka struct string. This here is a stack allocated variable. When our compiler is trying to write that assembly language code out to construct a stack frame, it needs to know how big that variable is. There, on line 9 in strings.h, all I've said is there is a type called string. You don't actually need to know anything about it. I don't want you to know anything about it. There's just a type that you can use that's called string. When our compiler gets to this point, it's kind of like, I don't know how many bytes I should be allocating on the stack frame for this type. So I'm not even going to try. I'm going to bail out. No, you cannot do this. So I'm going to make a tiny change here. I'm going to make this a pointer. This is now a variable called myString, where its value is an address. And if I follow that address, I should be able to find an instance of this type. It's a single character difference, but it means pretty different things. If I compile this again, I get an unused variable warning because I'm not using the variable for anything, but it compiles. On my stack frame, I know how big an address is. They're all the same size. All addresses on my 64-bit system, we're just going to say, for the sake of discussion right now, it's 64 bits. It's exactly 64 bits. It's not, and you'll find out why in operating systems, but for now, it's a 64-bit value. I've declared the stack variable. The stack variable itself is just the address of something that is a string, if I were to follow it. You might notice now that I can't say myString is equal to makeString. Because makeString does not return a pointer to a string. It returns an instance of that structure. So if I try to compile this one more time, incompatible with type. I can't assign a pointer to a string with an actual instance of a structure. So I'm going to make one more change here. In my public interface, I'm going to take this function and it will return a pointer. Compile this one more time. We get an unused variable warning, and then we get undefined reference to this function at the linker phase. That's great. I mean, it's never good to see an error, but this is good because we're now getting to the point of we have to provide the function definition here. So I'm going to open up strings.c. And in strings.c, I'm going to go down to my main function, and I'm just going to delete it. Strings.c does not have a main function anymore. Main.c has a main function. Strings.h does forward declarations. Strings.c is just going to have function definitions now. I need to change this code so that I'm actually implementing the function makeString. I'm going to comment out both of these function forward declarations for now, because after class, I want to have those comments to copy and paste. But when you see this after class, strings.c will not have these forward declarations anymore. I'm going to go back to the top of strings.c, and I'm going to say number include strings.h. So I'm including the same header file in both places. And I'm going to go down here to the make string function, and I'm going to change it to match the prototype that's here in strings.h. So it will not return struct string anymore. It will now return string pointer. Now, we're back in that same problem of you should not return a stack allocated array as a pointer. You shouldn't return that stack allocated string to the caller because the stack frame might go away. This here is a stack allocated instance of that structure. Within this code, I am allowed to do that because in strings.c, I have access to the full definition of this structure. In this file, all the functions know what the inside of a string look like. While I can do that, I cannot return a stack allocated structure to a pointer. I can't do that. So I'm going to change this code slightly. I'm going to delete this comment because it's no longer relevant. I'm going to delete struct string here. And we're going to reintroduce our old friend null. I'm going to change all instance of this, just lowercase string with my string. And then we're going to do one little fun thing here. We are going to do dynamic memory allocation. I'm going to say my string is equal to a new function that's called malloc. We're going to talk more about malloc later. Stack frames and stack allocated variables go on the stack. The stack is that very bottom part of our address space. At the very top of our address space was the code section. And then just below the code section was the heap. Malloc gives us an address. It allocates an address in the heap somewhere. The heap is shared kind of around the whole program. What malloc takes as input is how many bytes do you want right now? The way that we tell malloc how many bytes we want is to use the size of operator. Size of is not a function. Size of is not a function. It sure looks like a function, but it's technically and pedantically, and that's like the best kind of correctness in my mind, it is an operator. Size of will tell us how many bytes are in struct string. Struct string, or I can say string. How many bytes are in this structure? And if we go back to the top of this file, so I will come back to line 40 in just a second. If we go to the top of this file, in struct string, we have 100 bytes, 100 characters, plus 4 bytes for an integer. So we have 104 bytes for that structure. So you can get to a specific line in Vim very quickly by just pressing colon and then the line number, and that will just take you directly back to the line that you're at. So malloc size of string here says allocate a number of bytes in the heap that is the same size as the string structure. It's okay for us to return and then use heap allocated objects in other places, unlike stack allocated objects. That stack frame disappears. Our operating system does other stuff with that. Other functions get called. Those bytes are just going to get filled up with other functions. They're going to get changed underneath of us. We don't know what's going to happen with that. When I call malloc and I allocate something in the heap, that is reserved now for that object. So it will always be reserved for that object. Malloc is a function. So I'm going to quit this for a second. Man3 malloc. Malloc is a function that returns something called a void pointer, but it can return null. It's possible for this to return null if we don't have any space left on the heap to allocate. So just after I've called malloc here, I'm going to check to see if my string does not equal null. Only then should I start actually doing stuff with this. If malloc does return null, I don't want my code to crash, so I'm going to check to see that it has not returned null before I start doing stuff with it. With pointers, we unfortunately can no longer use dot notation to access properties of a structure. I'm going to introduce a new operator here. It's the arrow operator. It's just a dash and then a greater than symbol right next to each other. This operator is going to take the address that's stored in this variable, and it's going to do something called dereferencing it. So inside of this variable is some address, some hexadecimal formatted address, 0x77 something something something, like a bunch of letters and numbers after that. The arrow operator is going to go to that address and read its contents. And at that contents now is going to be the actual location in the heap that I can start doing stuff with, and that dash greater than symbol automatically does all of that for me so I don't have to think about it. And I have to change this one as well. Okay. So here is my make string function now. This is my whole make string function. It hasn't changed a lot. Structurally, it's still the same, but we've moved where this value is being allocated. We're checking to see that this memory that we've allocated has been allocated. This is, again, more defensive programming. We're still using strncopy. We're still assigning a value to this length as numchars here. Structurally, this is still the same. I'm going to save this. I'm going to quit that. And now I'm going to do the compilation process. I need to put all this back together again. The first thing that I want to do is I've got main.c, strings.c, and strings.h. Strings.c here does not have a main function anymore. There's no code in this file where I can start running stuff. This is just a library of functions. So I'm going to say clang wall strings.c. And I'm going to pass this -c flag. I want you to compile this code, but I don't want you to link it yet. It's not linked to anything yet. It's just a bag of functions. And then I'm going to say -o, and I'm going to say strings.o. This is an object file. So to my compilation, I've added this flag, -c, wall -c-o. Now in my directory, I've got 4 files, main.c, strings.c, strings.h, and the compiled version of strings called strings.o. I would like to stitch my main function into this now. So I'm going to say clang wall main.c, strings.o, not .c.o. I want to link these things together, compile main.c, and then link it with strings.o, that bag of functions that I've got. And then I'll say -o main. So I'm not doing -c for this one because it actually has the main function in it. My string is set but not used. It's an unused variable warning, but we've got a main program here. So I've extracted an interface into strings.h. I've extracted an interface into strings.h. I have got only my public interface here. So typedef struct string, no implementation details for what that structure looks like. I've got the forward declaration of my prototypes. I've changed the implementation of my constructor function to now do dynamic memory allocation. Allocate some memory on the heap. I'm checking to see if what I get back from that dynamic memory allocation is safe to use. It's not null. And I've added this new operator here as an arrow, this dash and then greater than symbol, to make sure that we can access something that is a pointer on the heap. All right. I'm going to pop over here, and I'm going to go to this next slide. Today, what we've done is we've defined an interface to an abstract data type. The abstract data type that we've got right now is a string. We've defined the implementation of an ADT with a private data structure. We've got this public interface that has a type declaration and then function prototypes with no implementation details. Separately, we've started to declare the type itself. We've listed those properties. We've implemented the function, but this is now in a separate file. My main function does not know how any of those things work. It doesn't know what's inside struct string. It doesn't know anymore. The private data structure here is, it's an array. That's the private data structure. My code that's using the library doesn't know that it's an array. It just knows that there's a type that it can use. We can design and use interfaces in C, specifically as a header file. We can hide implementation details of a data structure with headers and separate compilation. We can put those things all back together again, and we can use dynamic memory allocation in C. We can call the malloc function. We will return to this dynamic memory allocation stuff, but you can call the malloc function. You can start to do this. As I said, I will be posting a video for tomorrow's lecture. The topic is slightly different. It's not just a continuation of this. It's a slightly different topic. But I otherwise hope that you have a great day tomorrow. I will be on the farm. I will have some access to email in the morning and afternoon, but I'll otherwise see you all on Thursday. Bye, everyone.